Okay, so let's continue with our lecture materials. Last time we gave you a review, for some of you and then some new information for others about how we do hypothesis testing in the context of differential gene expression analysis. As I mentioned, for most so-called differential expression or DE analysis, we are interested in whether a gene, we call it gene J, has the same mean value under two conditions. And this mean is what we believe to be the true expression value. And under this null hypothesis that reflects our scientific question, that is, null means no differential expression, alternative means differential expression. We want to use our data to help us decide whether we want to reject this null hypothesis or not. And for this problem, the most classical statistic is the t-statistic. And last time we walked you through basically how the t-statistic was developed in the history. That is, we wanted to start by comparing two averages calculated from our data, but we want to consider the variance of such difference in averages because we know the data is not perfect. Then we calculate the variance and square root standard deviation, which is the magnitude of uncertainty we want to compare our difference of averages to. And then we need to get a ratio, right, for basically the average difference over standard deviation. But since the standard deviation involves a calculation of some unknown parameter, which is the variance of our gene expression under each condition, we need to do that estimation. And then what we did is that under the assumption that the gene has the same variance under two conditions, which is the t-test assumption, we pool the two variances together into a calculation of a pooled variance. And then we use that in our numerator, in our denominator as the standard deviation. Basically we pull the standard, we plug in the pooled variance square root here, and then this is our t-statistic formula. So with this t-statistic, the next step is to understand whether the value we observe means something significant. To answer this question, we actually have to derive the null distribution, which is the distribution of the test statistic under the null hypothesis. And here is the derivation, which gave us a distribution defined by our pioneers as the t-distribution. So which only depends on the sample sizes of the two conditions. We call them M and N. So this n plus n minus 2 is the degrees of freedom for a t-distribution. With this degrees of freedom specified, the distribution is fully specified. And then under this null distribution, we can evaluate whether the value we observe is something significant. Because I think this happens again whenever there is perturbation in my connection. Okay, so we're back to the camera. So this last step is what we call the p-value calculation, which uses the t-statistic value, the value we observe or calculate on our data, compare it to the null distribution, and we call the tail probability as our p-value. So whether we use just one tail or two tails together depends on how we specify the alternative hypothesis. Whether it's two-sided means that we are interested in anything other than equal means, or it could be one-sided means that we believe the gene is only interesting if its expression mean is higher in one condition than the other, like upregulation or downregulation. In that case, we will have a one-sided p-value. So that's basically what we did last time. But I also want to say that the null hypothesis, this mean equality, is just one thing. There could be other null hypotheses, and I will introduce one example today. Okay, furthermore, the test statistic can have varieties. T-statistic, the mean difference, average difference, is just one way to define a test statistic, and there could be other ways. For example, because if we believe that the distribution is symmetric about its mu, the mean value, then calculating the average from our data seems to be a reasonable way to come up with a statistic. But what if the distribution is not symmetric about the mean? What do? Right? So these are all the considerations we must bear in mind. And also, the t distribution under the null actually relies on either you assume your gene expression levels measure each condition follows a normal distribution, or you must have a large sample size so that then you can assume this average difference follows some normal distribution asymptotically. By saying asymptotically, we mean the sample sizes are big, so we can apply the central limit theorem to have normality. So you have to have either the data are normal-like, so you have small sample size, but you can still assume normal distribution, or the data may not be normal-like, but you have large sample size, then you can use asymptotic normal approximation. So either way. But what if for bulk RNA-seq data? So RNA sequencing is a technology that was introduced or developed in 2008, around 2008. At that time, the cost was very high. It's still not very cheap nowadays. I would say doing one bulk RNA-seq experiment, in the old days, it might be more than $1,000 to generate one sample. Now it is still more than $100 to measure one sample. So as I mentioned last time, you may not get a very large sample size. So you may only have n and n equal to 3, right? 3 replicates per condition. In this case, with such small sample size, then this central limit theorem-based result won't be applicable. And moreover, since your data are counts from RNA sequencing, you basically count the number of sequencing reads mapped to that gene in each sample. So for count data, it does not make sense to assume normal distribution, right? So for these two reasons, the t-test won't be a good method for analyzing differential expression for RNA-seq data. So just to move, okay, before we talk about the multiple testing, which is the end of my last lecture, let me switch the gear a little bit by introducing more test scenarios, especially in the RNA-seq data analysis, because I think that was a question we got at the end of the class, and also some people asked about the F test, which is another thing we hope to talk about today. So more tests, more DE tests. Let me put it this way. So let's talk about this RNA-seq data. So in this case, if I still look at my gene J, and I still call my data of the two conditions as X1J, XMJ for condition 1, and Y1J, YNJ for my condition 2. If that's still the case, then for RNA-seq data, there is a special thing we have to consider. That is, these data are counts, okay? And as integers, counts. So the normal distribution assumption does not seem to be reasonable, unless you want to do some transformation of your data and arbitrarily specify, for example, log counts to be normal distributed. But that is more like your arbitrary modification of the data. If we just directly work with counts, then normal distribution won't be reasonable. And furthermore, we have n and n being small, like 3. If that's the case, we cannot use the central limit theorem. So therefore, when people analyze the RNA-seq data, the two popular methods, especially developed for bulk RNA-seq data, single cell is another thing we'll talk later. They are HR. HR is a popular method. Another method is DE-seq2. So if you do single cell data analysis, you will most likely encounter these two methods in the tutorials. So they share a common assumption behind how the data are distributed. That is, they assume under each condition, X1J to xmj follows a so-called negative binomial distribution. This is a distribution we'll introduce later in our class. So just bear with me that for now we will ignore the details of this distribution, but just say it. So same as the normal distribution or Gaussian distribution, the negative binomial distribution has two parameters. You can still specify the parameter as mu1j, which is the mean of condition 1, and some variance. So I would just call the variance maybe sigma 1j squared. Okay, and similarly for condition 2, y1j to ynj, and I assume IID, independent, identically distributed. Another negative binomial distribution, mu2j sigma 2j squared. Okay, so here I'm not as restrictive as the t-test because I actually allow the two variance parameters to be different for the two conditions. Then the question is still with the same null hypothesis, that is mu1j equal to mu2j is my null hypothesis, while my alternative hypothesis is mu1j does not equal to mu2j. Okay, so both HR and DE62 aim to test this null hypothesis. And the difference between t-test and what they do here is that their test statistic and its null distribution will rely on this negative binomial assumption. So that is what they rely on and for their p-value calculation. So in the work that my group published, I think in 2022, it has received a lot of interest in the field, in the bioinformatics field, because we pointed out that if you apply HR and DE62 blindly to bulk RNA-seq data of patient samples, not experimental replicates, then there could be a surprisingly large number of false positives that you didn't expect. So why is that? The reason is actually in the negative binomial assumption. So basically, whenever this negative binomial assumption does not hold, then doing this test based on negative binomial will not really control false discoveries for FDR, which is a concept we haven't introduced yet. And also, you may have a large number of false positives. The reason is that the p-values, even if you can calculate p-value based on your null distribution, but the p-values are not satisfying its validity requirement. That is, the p-values must be uniformly distributed between 0 and 1 under the null hypothesis. So even though I haven't talked anything specific about the negative binomial distribution or how the test statistics of HR and DE62 were done. So this will be a topic we will defer to a later lecture. But for now, I just want to show you that this is an important assumption, and satisfying the assumption is very, very important. Otherwise, the test cannot give you valid result. But you may ask me this question. For a real data set, how do I check if this negative binomial assumption makes sense or not, right? If you just have 3 replicates in the typical scenario, my answer is you cannot check it because you have just 3 counts each condition and fitting a distribution, negative binomial with 3 counts, and you have 2 parameters. Then there's no way for you to say whether the distribution is reasonable or not. You just have to assume it because you have so little information in your data. And that was the scenario when the 2 methods were developed. You have such small sample size, but you also want to find some discoveries of DE genes. Then relying on some assumption that theoretically makes sense. And later when we introduce MB, we'll say why it's theoretically making sense for replicate data. Then you have to go with that, go with your assumption. But in the case that our paper covered, maybe I can show you our paper just to give you a sense what I was talking about. Just give me 1 second. In our paper, it is a different situation because we are looking at patient data. So let me put this here. So this is our paper. We're looking at patient samples, and the sample sizes are pretty big. So for example, in this first figure we look at, the sample sizes are actually 51 and 58 under the two conditions. It is from an immunotherapy data set. 51 patients before treatment, 58 patients on treatment. So in that case, we can check how well do our fitted negative binomial distribution describe the 51 counts and 58 counts. So we can check that. So let me just quickly show you one result to say why we believe there's a lot of false discoveries. So the finding is actually very intuitive. What we simply did is that we randomly shuffled the two groups by keeping their sizes of 51 and 58, but the values are randomly shuffled. We can do such permutation for many times, like 1,000 times. And we just perform the DE test on each permuted data, record the number of DE genes, and then we get a distribution. This is the bar here. So we can see that the red dot indicates how many DE genes were identified from the original data. And this error bar and the height is the average number we get from permuted data. And the error bar is the standard deviation from permuted data. So you can see that from the permuted data, from many permuted data, we get even more DE genes than from the original data. And this must indicate something wrong, because for the permuted data, we know the two group labels are just meaningless. So this is how we discover it. But the underlying reason why this happens is because of the negative binomial fitting. So let me show one example. Maybe it's not in the main text, but it is a figure I hope to show you in my talk. So this is the paper I can post to the website, our website, so you can take a look later. But in my opinion, it's like a cautionary message that when we use our methods, we cannot use them blindly. There could be ways for us to do some sanity checks, and it's important for us to do that. So otherwise, we don't know whether we can trust the result. So
Jessica?
Yes, just give me 1 second before after I show this. Yeah, so I just want to say that this is what we call the quantile plot to check how well the distribution fits. And this is in the supplement figure. Basically, going to show that on for this particular gene MXD1, the fitted negative binomial by edge R and by DE-sig2, this is DE-sig2, do not agree well with data, because if they do, the points here that represent the values of the gene in each condition, pre-therapy, on therapy, should lie on a straight line instead of having so much offline dots. Yes, your question.
I just wanted to confirm. So you said that the biggest reason why we see the difference is because we have a lot more samples when we have
a lot more samples to plot this. If you just have 3 dots, then you have 3 dots here, right? So it's hard to say whether the line fits well or not.
Okay.
Yeah. And also, if you have just 3 values, there are not so much permutation you can do, right? There are only so many ways to assign 6 values into 2 groups. Yeah. Thank you for the question. Yeah, so, and you can see that in our title, basically we emphasize that the difference is here. We are looking at human population samples from patients, not experimental replicates. So this is another crucial thing to bear in mind, that the data you analyze can differ, right? And whether the assumptions let me close this up, for a popular method holds for your particular data set. That is very important. So permutation is a very, very powerful technique for us to do sanity checks for our own data set. So hopefully, maybe next Wednesday, you will listen to a talk I previously recorded about how to use permutation in some examples. So yeah, so I'll just be brief here to say that we should bear in mind that the assumptions matter. And if the assumptions do not agree well with our data, a popular method may give us a lot of false positives. That's the take-home message. So another thing I want to say that when we find that okay, when this negative binomial assumption does not hold on our data, and using these methods can give us false positives, what is the remedy? What is the alternative approach? And let me pull up my slides here again, which is what I just showed you here. Let me pull this back here again. So in this plot, we show that Wilcoxon rank sum test is a classical method that doesn't have inconsistency between original data and permitted data. So basically, it consistently has 0 discoveries on both original and permitted data. So while this may not be something of your interest since you want to look for DE-genes from your data, however, this consistency to me at least is less worrisome than having this inconsistency, right? More DE-genes from permitted data than original data. Then what does Wilcoxon do? Why do they have very different results? So let me just go here to look to the Wilcoxon. And this is what the null hypothesis is for Wilcoxon. That is, it's not directly comparing two means as we have for the negative binomial. So maybe I can pull this up a little bit and just write here on my paper. So Wilcoxon rank sum test is well known as a non-parametric test. What does that mean? So when we say it is a non-parametric test, we mean that it does not assume a parametric distribution. So the previous two examples we said normal and negative binomial are both parametric distributions. So Wilcoxon doesn't assume this. Instead, what's its null hypothesis? Suppose that you have two sets of values, right? So let me just write here, following our notation. So if we are comparing x1j to xmj versus y1j to ynj, two sets of numbers, to see if there are any systematic differences, and we don't want to assume a distribution for each one. Then its null hypothesis is basically what's here. The null hypothesis is that if we randomly pick one x something j, okay, I don't know what it is. I just randomly pick one out of the m and one y something j. So from the second cohort, one value out of the n values. Then which one is bigger? Which one is bigger is equally likely. Then the probability that this x dot j is larger than this y dot j is 0.5. Means that equally likely which value is bigger. So this is the so-called rank-based null hypothesis. It is not concerning the mean of the mean values of the two distributions, because we're not specifying distribution out. We're just talking about the relative magnitude between the two sets of numbers. So it's a different null hypothesis, but this null hypothesis has less reliance on the mean equality. And I have to say that if we are under the t-test setting, that is, we believe that the two sets of numbers each follow one normal distribution with the same variance and just potentially different means, then this Wilcoxon null would be equivalent to that equal mean null. So in that setting, they are equivalent. So having this equal rank order means that the two normal distributions have the same mean parameter. Okay, but it does not assume that normal distribution. So that's why you can see that people call this Wilcoxon non-parametric test to be more robust to model misspecification. This is another jargon I hope to introduce to our students. So model misspecification means that the distribution we assume for our data, for example, negative binomial, is not proper. It doesn't describe our data well. And there is a chat. Is rank-based null always less biased than parametric test? Okay, good question. So I would say bias is a term we should be a little careful when we use, right? Because in the statistical language, when we say a bias, it must be relative to some ground truth. And in this case, here we can say it's biased when there's model misspecification because the model is a biased model. It doesn't describe our data well. So in that sense, yes, you can see Wilcoxon, well, I would say it is more robust to such model misspecification. But in statistical method choice, we have to be aware that there's no free lunch. You always have to pay some price. And here the price we pay for gaining this robustness of by not assuming a parametric distribution is that we would be less powerful if the normal distribution assumption for t-test or the negative binomial distribution assumption here for the count data is correct. So when these distributions are reasonable, but you are not assuming them, you are going with Wilcoxon for not assuming much, you lose power. So that's the price you pay. And that's why for small sample size, like m equals to n equals to 3, let me turn this off, you may not have any discoveries using Wilcoxon. And that's why biologists are not happy about, because they want to find something from the data. But if your data sample size is large enough, like in the 51-58 case, it is some scenario where your data itself contains enough information, then you can afford to assume less in your approach. So I would say assumption and data always go hand in hand. You have to make a choice, because if your data is just small sample size, scarce information, if you want to make some discoveries, your assumption is necessary. You have to assume more to get some results, right? But on the other hand, if data itself has rich information, you want to assume less to be more unbiased, quote unquote. So that is the general thinking for method choice. So at least after this class, I hope our students can have this feeling or understanding that there's no single method that is always optimal. So this is very, very different from our experimental protocol choice. Many cases you would say, oh, with our technology advances, I would go with single cell data, maybe not bulk data, or with bulk RNA-seq data, maybe I won't use microarray anymore. So for experimental technologies, this choice seems missing more obvious, but for computational approaches, I don't think that's the case. So every method should have its own suitable data set. And how to choose that method given your data, that's the most challenging question. Okay, and another question. Okay, thank you. So let's continue. So I said,
Professor, I have a quick question.
Yes.
In the figure that you showed previously, lemma voom also didn't have that much of an issue when it came to false positives, and I know that in addition to edgeR and dseq2, lemma voom, at least using those packages in combination, is also a common strategy that people use. So is there a reason why lemma voom performs better than the other packages?
Yeah, good question. So I would say lemma was a method that was developed for microarray data. And microarray data, it can be reasonably assumed because the values are continuous. It can be assumed to follow normal distributions. So lemma is basically a linear model based method that assumes the errors to be normally distributed. And voom is an approach to adapt that to count data to RNA-seq data. So you can think of this as you transform count data to satisfy normal assumption, and then you apply a normal based test. So in other words, compared to the negative binomial direct modeling approach, such approach, which is something we would introduce later, log transformation is an approach to reduce outlier larger values in your data to make your data more concentrated on its mean after log transformation. So therefore, you can say it is more robust. than based on the count distribution negative binomial. Yeah, that's another thing to think about. So intuitively, people might think direct modeling of the data is more desirable because you're doing less arbitrary modification to your data. But then the count distribution, especially like negative binomial, fitting it, estimating two parameters is not a trivial task compared to normal distribution. So therefore, it could become less stable because if you have some outlier counts, large positive count, then the negative binomial parameter estimates may change a lot if you just change one value. But if you do log transformation and fit a normal distribution, it will be less sensitive. Yeah. Thank you for the question. All right, so let's come back to the discussion. So basically, there can be multiple choices of your null hypothesis, parametric or not, and then test statistics. And furthermore, let's consider going back to the t-test, right? So I think I want to answer a question we got at the end of last class, which is about the equal variance assumption of t-test. So this is the question. Equal variance assumption of the two sample t-test. Okay, so for this, if we just write it out again, it is assuming that x1j to xmj, they are IID, normal mu1j variance sigma j squared. So we still have to carry j for g and j. While y1j to ynj, IID, normal distribution mean mu 2j sigma j squared. Okay, then the question, why common sigma j squared for the two conditions? Right? That's the question. Okay. And to answer this question, we would actually need to, maybe you will say, why cannot this be a test problem? Can I have a null hypothesis to say, oh yeah, if I write it as sigma 1j squared for condition 1 and sigma 2j squared for condition 2, can it directly have a null hypothesis for this and an alternative hypothesis to say that they are not equal? So if I would not accept this null hypothesis, or if I reject this null hypothesis, then probably this t-test assumption is problematic. You could ask this question. And so in this case, we would have the f-test to tackle this problem. So the f-test is basically what we call a ratio, the test statistic. Okay, we call it f. The test statistic f is defined as the ratio of the two sample variances. So which is sx squared over sy squared. Okay, and each sample variance can be calculated as their unbiased estimate for sigma j squared. So basically, for the first sample is n minus 1 as the numerator, and the summation i from 1 to n, xij minus xj bar squared. And xj bar is just the average of these n values. And similarly, for the second sample, we will have an estimate for variance as 1 over n minus 1, sum I from 1 to n, yij minus yj bar squared. So it's the ratio of the two. And under the null hypothesis that these two variances for the two samples are equal, we actually can say that under the null hypothesis, the distribution of this f statistic is an f distribution whose degrees of freedom is n minus 1 and n minus 1. So like t-test has 1 degree of freedom, F distribution has 2 degrees of freedom, which is basically the degrees of freedom of the numerator and denominator. How to intuitively understand this? So basically, in the numerator, right, when we compute the variance, sample variance, so basically the variance we calculate from the sample, we have removed 1 degree of freedom by shifting everything towards the center. So basically what I'm saying is that you have the center, the average here, and you're only looking at how each point is around its center, right? We're taking the difference. And doing so, we no longer have n values that can vary freely because the center is basically fixed. So it's just like I can shift the center to 0 for everyone, and then this difference will remain the same. So that's where the 1 degree of freedom is lost. We fixed the center, and similarly for the numerator. So therefore, for each sample, right, as we calculate the sample variance, the degrees of freedom has been reduced by 1 for each. So we get n minus 1, n minus 1. And just like the t distribution is a manually constructed distribution for our convenience, for p-value calculation convenience, the F distribution is the same. So this distribution, as long as you specify 2 degrees of freedom, they're called the numerator degrees of freedom and denominator degrees of freedom. As long as you specify them, you can get the distribution. So in the old days, people can just make up a table for F distribution, right? Given the 2 degrees of freedom. And then you compare the value for this F statistic on your data to the corresponding quantiles of the distribution in the table, then you get a tail probability, and you call that the p-value. So in other words, the F distribution has its values ranging from 0 to positive infinity, and basically it will have a density function something like this. So let's just call this f n minus 1, n minus 1. Okay, and suppose that your observed value for f lies somewhere here. If this is the value you observe for your data, then the right tail probability here, what is the probability to the right of your observed value, is what we call p-value. And then you will compare this p-value to your pre-specified significance level, maybe 0.05. Then you decide whether you want to reject this null hypothesis. Because if this f is too big, so if the ratio is too big, is 2 in the right tail, then probably you would say, yeah, I think this means that my sx squared is much bigger than my sy squared. Then I will not accept this null hypothesis. But you see, the right tail may not be the only thing you want. Since the ratio, if it's too small, you may also have this question, right? Whether this is something too small, that's sy squared, much bigger than sx squared. So therefore, to have a two-sided test like this, then you also need to consider here, this is 1 over f, the inverse of that. So basically, if this ratio is very big, then this is larger than 1. Its inverse is less than 1. So then you also need to get the left tail here. So both tails together will give you p-value, depending on whether you want to go one-sided or two-sided. So whether you have 1 over f here, or f here, 1 over f here, that depends on whether the value you observe for f is bigger than 1 or smaller than 1.
Professor, I'm sorry, can I clarify something?
Yes.
So, like, S is like sigma squared, right? But, like, so, like, the sum of x minus x bar over n minus 1 is sigma squared for n, right? So that's just the ratio of sigma squared.
So yeah, so the thing is that to derive this, we actually need to have so basically for an F distribution definition, it is a chi-square random variable divided by its degrees of freedom over another chi-square random variable over its degrees of freedom. And the two chi-squares must be independent. So that's the requirement. And to have chi-square random variables, we have to start with standard normal random variables. And to have standard normal random variables, we need to divide sigma j squared, both numerator and denominator. But the thing here is that since under the null hypothesis, the sigma j squared is the same for both samples, so we can cancel it out. So that's why in the F statistic ratio, there's no sigma squared. That's my answer to your question, if my understanding is correct.
Okay, thank you.
Thank you. Thank you. Okay, thank you very much for your good questions. And also, I want to say one more thing besides this F and inverse F. So one property we know about F distribution, which is something important to know, is that if F under the null hypothesis follows F with degrees of freedom n-1 and n-1, then 1 over F, the inverse, would follow also an F distribution with the 2 degrees of freedom swept, which is also a nice property to know. Okay. All right, so that's the F test for comparing the variances of two samples. So finally, I want to say that there is a very general approach if you have enough computation power, which is permutation test. So the permutation test idea is that we don't need to mathematically derive the null distribution for our test statistic. Say that you have null and alternative setup, okay? And you have test statistic T setup. So this could be T statistic, it could be Wilcoxon test statistic, it could be F statistic. So many choices you have. But here the challenge is, how do I derive the null distribution of my test statistic? If that's your question, and if you have the computational power to do permutation, this is what you can do to basically numerically simulate the null distribution by permuting your data. So the strategy can be very general, and it is something we can do everyone by ourselves on our computer. That is, from the original data, let me put it as two samples, right? X1J to XMJ, Y1J to YNJ. So N values here, N values here. So what permutation does is I shuffle my values, but I still keep the sizes as N and N. So basically I can do B permutations independently. But this would of course require N and N to be large. Otherwise, there are not so many possibilities for your permutation. Okay, and if you do that, what you can do is to just calculate the permuted data by shuffling the labels. You just randomly choose N out of the N plus N values and assign them as group 1 and the rest as group 2. So suppose that I can have B such data sets, okay? And I can call them as X1J1, XMJ1 as the data from my first permutation, YIJ1 to YNJ1, okay? And so on to my B permutation, X1J capital B, XMJ capital B, and Y1J capital B to YNJ capital B. And from each permuted data set, I could compute my test statistic value. All right, so let's say that from this original data, I calculate the value for my t. I call that small t. It's the value from my actual original data. And from each permuted data, I just calculate the value, and let me call that T1 from the first permuted data, and sorry, TB from the last permuted data. So if we think the permutation basically satisfy my null hypothesis, if that is what we believe to be, then we have T1 to TB follow the null distribution, right? Null distribution of T. So if the null hypothesis holds, then my test statistics should take values as T1 to TB. So if we believe that, then this T1 to TB is basically a numerical representation of this null distribution. So this idea of realizing a distribution as a set of values from that distribution is known as Monte Carlo. So Monte Carlo, the name stands for that. So you numerically sample values from that distribution and use the sampled values to represent that distribution. Here, if we believe that permutation satisfies our null hypothesis, this is what we do, okay? Then the p-value calculation is basically comparing your observed value small t to this set of values from the null, and then you get a p-value. So for example, if more extreme, so the p-value calculation will have this saying of more extreme, right? So if this more extreme means larger, it could be smaller, or it could be absolute value being larger. Either way, depending on how you define more extreme under the alternative scenario, the p-value can just be defined as the proportion of those capital B null values that are bigger or equal to the observed value t. So that is, we just look at the proportion of this T1 to TB that are greater or equal than our observed T. That's basically it. And we can, okay, sorry, just touch this again. And okay, we're back. And this actually can be written formally as 1 over B times the sum, let me say small b from 1 to capital B. And for each small b, the small b permuted data, I look at this indicator function to see whether this t of small b is greater or equal than small t, right? As long as this satisfies, I count 1, otherwise I count 0. And this total is the number of null values greater than t, greater or equal than t, and I divide the number by capital B as the proportion. Okay, this is the permutation test. But some people may want to do something by adding a small constant to both the numerator and denominator. The reason is they want to avoid exactly zero p-value. That's why they want to do that adjustment. Because if you have this definition, a naive definition, if this t, small t, is larger than everything we simulate from the permutation, then you will get a zero p-value. And people may not like that. So that's why they do adjustment just for that purpose. Okay. But this permutation test is very, very straightforward. So you just need to know how to simulate data based on the original data under the null hypothesis. So permutation can be one approach, but it may not be the only approach. The whole idea is to do this null distribution generation numerically instead of mathematically. Okay, so any questions so far before we continue? I think that's what I hope to say for doing one single statistical test for each gene. And as a result, we will get one p-value for each gene. Okay, so if you don't have questions for now, then we will continue with our next topic, multiple testing correction. So just for your information, since we are doing remote teaching this week, my office hours for today at 5 to 6 will be using the same Zoom link as this one. Okay, so for type 1 error, we said last time, right? So it's basically under the null hypothesis, what is the probability of having the p-value less or equal than the significance level? If the p-values are well calibrated, which means they're valid p-values, then the p-values should follow uniform 0 to 1 distribution under the null hypothesis. So this type 1 error should be equal to significance level. Sometimes you may have the p-values not perfectly calculated, but if they are in the situation where the p-values are more towards 1 than 0, then you're still okay, because in this case, the type 1 error will be less than significance level. So you're still okay with controlling type 1 error, but just being conservative, and you lose power. But you will have problem if your p-values under the null are concentrated around 0. Then in case you have too many small p-values, even when the null hypothesis holds, then your type 1 error can be much higher than significance level. So you fail the type 1 error control. Okay, so p-value distribution check is very important. So if you have one p-value per gene in your DE analysis, then a very easy check is to plot all the p-values as a distribution and then see whether the majority of your p-values seem to follow a uniform 0 to 1 distribution. So that, but of course, that is under your hypothesis that only a minority of genes are true DE genes, are the signal, and the majority are negative cases or null cases. So under that, you can plot and check. And you can also plot the QQ plot, quantile plot, for the p-values against uniform 0 to 1 as the theoretical distribution. And you can see whether your p-values, most of them lie a straight line, and only a minority of them are not. So when people do that p-value check, what is commonly done is this. So let me just say this. Maybe I should quickly introduce what is a QQ plot. So p-value validity check. So basically, under the assumption that most p-values are from the null hypothesis, and the p-values are largely independent. Independence is so important because otherwise we cannot tell from the data. For example, what is extreme scenario of the extreme scenario of dependence? That is everything being identical. So they are fully dependent. Then in this case, observing p genes p-values is the same as observing just one p-value, right? Because they're all equal to each other. Then you cannot tell what the distribution is like. So that's why having some sort of independence is necessary. So you can see the distribution. And also, under the assumptions that most p-values are from the null, so you would expect that if I plot the p-value distribution, if this is the 0 to 1 interval, if I plot the p-value in statistics, we say empirical distribution, which means that you're just plotting a distribution based on your empirically observed p-values. And like p-values for p genes, we are pooling the p-values together into like a histogram or density plot. You can do a for example, histogram. Then if the p-values are well behaving, right, satisfying this assumption, you know that you may have a small spike near 0, indicating the true signals, the genes that are interesting. But for the majority of genes, the histogram should be somewhat flat. So as you get away from 0 and reaches 1, right? You should have a somewhat flat histogram to indicate that this uniform assumption is holding for the majority of p-values, and the small spike indicates signals. So this will indicate a well-behaving p-value histogram. But what would be not good? That is, if you have a clear distribution where many p-values are around 0, and you have very few larger than 0, and you don't see a uniform trend, and that will be problematic. Okay, and one more thing is about quantile plot. So if you want to do quantile plot, it is again, it basically what this does is comparing an empirical distribution based on our data distribution versus a theoretical distribution, such as the uniform distribution. We compare the two distributions, and we compare the quantiles of the two distributions. So what does a quantile mean? Let me use uniform distribution, maybe normal distribution, a better example. So quantile means, say, if this is a normal distribution, so if the left tail here is 0.1, okay, then I can call this value, corresponding value, as the 10th percentile. So that's the definition of quantile, depending on how many values we expect to be less or equal than this value under what distribution. So for uniform distribution, the quantile is exactly equal to the probability of the left tail. Say if it's 0.1 here, the value should be 0.1. 0.5 here, the value should be 0.5, right? So they're equal to each other. So to plot p-value against the theoretical uniform distribution, how do we do a quantile plot? We actually usually take negative log p-value to do the plot. Okay, and why do we do that? The reason is that p-value has a very small dynamic range, just 0 to 1. But once we take the log, we can get negative values, right? And log 0 is what? Negative infinity. Log 1 is 0. So we can get a range from negative infinity to 1, which is to 0, which is a much bigger dynamic range. And we add a negative sign to make it positive. So the range becomes 0 to positive infinity. So we're comparing such negative log p-values to what we expect for the quantile in the theoretical uniform distribution. So in other words, a small p-value closer to 0 will give me a large positive negative log p-value. So then in the quantile plot, basically for that, maybe we will say this is the theory. This is the empirical thing. And then we will expect a straight line. That is, the theoretical quantile and empirical quantile perfectly match each other. But what could happen is that because you expect to have, how to say, more small p-values around 0 than uniform 0 to 1. So transforming to negative log, what does that mean? You expect to have more large p-values than the theoretical one. So having more large p-values, how would that affect our quantile? So suppose that, let me just plot one plot to help you understand quantile plot. So one line is what we have empirical distribution. Let me call this negative log p-value. So I have some large values in the right tail to mean that these are the original very small p-values here. On the other hand, I have a theoretical distribution uniform 0 to 1, and that will be more light tail. So I'll just use the dash to draw that distribution. So if I just quickly decrease in the right tail, that means the theoretical one, and this is the empirical. The theoretical one has less light tail, less right tail, means less large values. So therefore, if I go with, and they are mostly the same, I would say their difference is not this big, but I want to say for the majority of them, they are similar. So that's why we have a straight line. But when we calculate quantile in the tail part, right? So for the same large probability to the right, to the left, say 0.9 on the left, then maybe I need to go further to the empirical distribution to have 0.9 than in the theoretical distribution. Okay, so both 0.9 probability on the left, but here theoretical I come to here, but for empirical I come to here. So that means empirical quantile will be larger than theoretical quantile. So in this case, if I look at the QQ plot, most of them lie close on the line, but maybe in the right tail for large values, I will see something upward to indicate that the quantiles in empirical distribution will be larger than theoretical distribution. So this is what you should expect for a well-behaved p-value QQ plot. Okay. All right. But I would say if you don't expect there to be too many discoveries, this deviation won't be that obvious. And the majority of p-values should lie closely on the line. Okay, so that's p-value. Once we have valid p-values, then next step is to actually get our, multiple testing correction. Okay. And you may wonder, why do I want to do that? So the question is what we introduced at the end of the class. So even though you can control type 1 error well, for each of your observation, for each of your genes, for each of your gene, you may control the type 1 error, say under 0.05. That means if the gene is not a D gene, there's a 5% chance you may wrongly call it a D gene. But if you have tens of thousands of genes, so in this case, if you have, let me just make it up, 10K genes, right? That's a reasonable number for the human genome, because in human genome, protein coding genes are more than 20K. So if you have 0.5 chance of making a mistake for each gene, and suppose that 90% of your genes are not D genes, right? Majority of them not D genes. Then you make a false positive discovery number. I would say the expected number of false positives would be 0.9 times the total P, which is 10K, times the mistake probability for each gene, 0.05. So that will give me this number. And if I multiply by 10K, it will be 450 mistaken false positive genes. So to many people, this might be too many, right? So 450 false positive genes will waste my experimental validation. Then what do I do? So I would say this is where the multiple testing problem begins. So the so-called multiple testing problem means that we are concerning about the total number of false positives. And this number can get large even though the false positive or type 1 error mistake for each gene is low. As your gene number gets high, the total number will get up. Okay, so for this case, if we draw a table, which is like decision table, so you know what we're talking about. So in this case, we will have the rows as our decision. Okay, so we have two decisions: reject, null hypothesis, do not reject, null hypothesis. That's our binary decision. And the two columns we have is the truth. Even though we don't observe it, but we believe that there is some truth, right? This is about H0 null hypothesis being false, or the null hypothesis being true. So suppose that we have a total number of, so just to be a little bit consistent with the type notes I posted online. So suppose, oh, I will post this online. So suppose that we have a total number of M genes. Okay, just we change this notation a little bit because the P is used for P value. So here we just say we have M genes. Then regarding the truth, we will say M0 genes are M0 genes are false. Let me see, I think it's, oh, sorry, I should put it here. M0 genes have the null hypothesis holds, so they're true. So then the rest is M minus M0 that have null hypothesis false. And regarding our decisions, so if the null hypothesis holds that we falsely reject H0, we denote the number of genes by V. That's our false positive. And this one, if the null hypothesis is false, but we do not reject it, we make a false negative call, and we call this T. So these are two mistakes. And there are things we do correctly, and we call them S and U. So S means that for the false, the true positive, right, where this H0 is false, so alternative holds is true negative, and we do that correctly. I'm sorry, true positive. True positive, we do that correctly. And U is true negative. So the null is true and we didn't reject it. Okay, and we also denote the total number of rejections as R. And then this is M minus R. So notation-wise, please pay attention that the way we draw this, when we write it, has used both capitalized letters and lowercase letters. So for the uppercase capitalized letters, we are trying to say they are random numbers, random variables, because our decision depends on our data. And if we consider our data to be a random sample from a population, then the decision is random. So that's why anything related to our decision must be capitalized notations. But the ground truth, like which null hypothesis is true or not, is not random. It's the ground truth. So we use lowercase. Okay, so with this notation, I think our discussion will be much easier. Okay, so basically, we can define 3 criterion to quantify our decision errors in multiple testing. And we focused on the false positive errors. That is, when the null hypothesis is true, we make false rejection. So I'll just say we have 3 criteria. The first one is called per comparison error rate. So PCER. So this one is basically our type 1 error. So what is defined, but it's in a multiple testing setting. So it's just average across our M comparison. So we'll say that as for M genes, we have M tests and M comparisons. All right, so this PCER is defined as the expectation of B, number of expected false positives out of true negatives. Okay, or actually I should say, maybe, no, I think my bad. Out of total number comparison, it's per comparison. Okay, and this one, because M0 is not observed, M is observed. So maybe I should say this. So M0 and minus M0 are not observed. Okay, and actually this whole table, S, V, T, and U are also not observed because they require the knowledge of the ground truth. But our number of rejections R and M minus R are observed, right? We know how many rejected. So these two are observed. So these are the things we have to be clear. So PCER is defined as expected value of V over the total M. But as we know that n cannot be greater than m0. M0 is just a subset of the m comparisons. So we know that we can have this less or equal than EV divided by M0, which is the expected number of false positives out of true negatives. And this is what? This is exactly our definition of type 1 error, right? Because this EV is equal to M0, number of true negatives, multiplied by the chance that each one is mistaken, and multiplied by the significance level. Alpha is the significance level, divided by M0 is alpha. So in other words, if we are just interested in controlling the per comparison error rate, setting p-value to alpha, setting p-value threshold to alpha is enough. So basically, compare, or I should say, setting p-value threshold to alpha is sufficient to control the per comparison error rate under alpha. That's it. If you just want to control this criterion, you're good. Just compare it to 0.05 if that's your significance level. But as we said, this is not enough if you want to control the total number of false positives. That is V. The V can still get, so this expectation of V can still get very large, right? M0 times alpha can still get very large. So on a more stringent side, we have another criterion called family-wise error rate. And this is in short as FWER. Okay, this is a very stringent criterion as it is defined as the probability that this V is not zero, larger or equal than 1. So it means that as long as you make one total false positive discovery, you satisfy this event and it has to be accounted for. So it is the probability of making at least one false positive discovery. So basically, in our cases, DE gene is that out of your DE gene list, there is at least one gene that's false positive. Okay, and it's very stringent, but how do we control it? So for this one, we will use a very commonly used operation in probability theory. That is, the probability of a union set is less or equal than the sum of the probabilities of individual sets. So we'll use that, and we'll stop after we introduce this. So basically, this probability can be written as a union because we can just go through each gene at a time, right? So we can say we take the union of the sets of J goes from 1 to M, and to say that gene J is a false positive. I just use FP to stand for false positive. So we just check every gene in our result. If gene J is a false positive, the event happens, and then the union happens. Then that's where V is greater or equal than 1. And as I said, this is commonly bounded by the sum J from 1 to M, the probability that gene J is a false positive. Okay, and gene J being a false positive is controlled by what? Type 1 error, right? Or significance level. So that controls that when gene J is a null gene, the probability that is discovered as a D gene is only alpha. So basically, this is alpha. sum for n times. So this is n times alpha. So which means that if you want to control family-wise error rate under some Q, let me just say, so if we want to control family-wise error rate under some target Q, say 5%, it is sufficient to set alpha, the significance level or the threshold for p-value, to be Q over n. If you do that, then family-wise error rate will be controlled under Q. So this is known as Bonferroni correction. Okay, and you can see it's how it can be very, very conservative, because if your Q is 0.5 and M is 10,000, then this will be an extremely small number, and you may not have p-value less or equal than that. So therefore, you may not have any discoveries. So biologists are still not happy with this because it's too conservative, and maybe where our goal is not so strict, right? We can allow for some false discoveries, not necessarily zero. So therefore, a criterion in the middle between this loose PCER and the stringent FWER is called false discovery. So that is something we will introduce in our next lecture on Wednesday. All right, so that's all for our class today. And I'll see you on Wednesday. And if you have questions, please come to the office hours at 5. Thank you. And please stay safe.
Thank you.
Thank you.
Thank you. Have a nice day.
Thank you.
You
Thank
too.
you.
Thank you. Thank you. Bye.
Bye.
Bye.